Hello everybody, this is Michaela Mooney doing Vertex Edge Graph 7 Discussion Assignment Part 1. And today we are going to use the greedy coloring algorithm for coloring vertices of graphs. And let's just jump straight into it with question number 1. Question 1, we are going to use the greedy coloring algorithm with alphabetical ordering for the vertices to color the vertices of each of the graphs. For the vertices to color the vertices of each of the graphs. And I went ahead and wrote out all of the steps that we're going to be using for the greedy coloring algorithm. And let's just take a look at what those are. So first we have to choose an order for the vertices. And it already says in the question that we need to use alphabetical order. So I wrote out the alphabetical order. And then number 2, we need to choose a list of colors also in some order. So I went ahead and chose this list of colors right here, and I numbered them in the order that we'll be using them. And they also happen to be in Roy G. Biv order, so that makes it easy too. And then step number 3, this is where we get into actual direction of what we're going to be doing on the graphs. In order, color each vertex using the first legal color on the list, making sure that no two adjacent vertices are the same color. So a legal color is going to be a color that makes sure no two adjacent vertices are the same color. So like if this one is red, then neither of those three can be red, because red would not be a legal color for those three vertices. We'll get more into that as we're going through our steps on the graphs, but just keep that in mind. And then step 4, we're going to continue in this way until each vertex is colored. So let's go ahead and jump right into it. And so we're starting in order, and the first vertex in our order is Vertex A. And our first legal color is going to be red, because that's the first color on the list. And there's no other color on the graphs. So our Vertex A is going to be red. After that, we move on to Vertex B, and B is touching A, E, and H. And A is already red, so that means it is not a legal color for B. So the next legal color on the list would be color number 2, which is orange. So we can go ahead and color B orange. Up next, we have Vertex C, and C is touching A, F, and I. And A is red, so red is not a legal color for C, and just like B, it is going to be orange. Next, we move on to Vertex D. D is only touching Vertex H and I, and neither of those are colored yet, so that means our first legal color is color number 1, which is red. After D, we move on to E. E is touching a bunch of vertices. It is touching B, A, F, I, H, and G. But the only ones we're really worried about are the ones that are colored, so we're worried about A and B. And those two vertices are red and orange, so neither of those are legal colors, so we have to add a new color, which is number 3, yellow, which is a little hard to see, sorry about that. But E is going to be yellow. So we're up to 3 colors now. After E, we've done A, B, C, D, E. We are on to F, and F is touching E, I, and C. I is not colored, so we only have to worry about E and C. And E is yellow, and C is orange. So that means the first legal color is not going to be green, because red is on the list. You might think about adding green first, because you think, oh, we've used red, we've used orange, we've used yellow, the next color on the list is green. But you have to remember, it's not touching a vertex that is red. So that means red is going to be our first legal color. So F is going to be red. After F, we move on to G, and G is touching E, H, and I. And the only color it is touching is yellow. So if that's the only color that's illegal, we can say, then the first legal color, like F, where it's not touching red. So that means red is still a legal color. So for G, it's also going to be red. After G, we move on to H, and H is touching G, B, D, E, and I. And so, if we look, it is touching B, which is orange, G, which is red, and E, which is yellow. So that means all of those colors are not legal. So we're going to add another color, green, to our list. So H is going to be green. And finally, we have vertex I, which is touching all sorts of things. It's touching C, F, E, G, H, and D. And it happens to be touching orange, red, yellow, and green. So it's touching all four of the colors we've used so far. So we have to add another color, color number 5, which is blue. So now we can go ahead and number the colors that we've used with the color they are on the list. So reds are all going to be 1, because red is color number 1. Oranges are color number 2. Color number 3 is yellow. 4 is green, and 5 is blue. So we have used a total of 5 colors on that graph. Let's go ahead and look at graph number 2 and see how this one turns out. We're going to use the same exact greedy coloring algorithm, same order of the vertices, same order and colors. Same order of the colors, same exact colors. So we're going to start with A, and there's no other color on the graph, so we're going to use our first legal color, which is red, for A. And then after A, we look at B. B is touching A, so that means red is no longer a legal color, so we have to go on to our second color, which is orange. Next, we move on to C. C is touching both A and B, so red and orange are both not legal colors, and we have to add our third color, which is yellow. So C is yellow. After C, we look at D. D is touching A, B, and C. So red, orange, and yellow, none of them work. We have to add our fourth color, green. D is green. And finally, E is touching A, B, C, and D. So none of the colors we've used so far are legal, and we have to add our fifth color, which is blue. So if we go through and number all of them, red is 1, orange is 2, yellow is 3, D is 4, blue is 5. We have used 5 colors for this graph as well. Now, if we move on to question number 2, we are going to use the greedy coloring algorithm with reverse alphabetical ordering for the vertices to color the vertices of each of the graphs. So we are going to be using same exact steps, same exact rules, same exact colors, except our order is going to be reverse alphabetical order. And I wrote that out because I am not good at reverse alphabetical order, so I'm going to be using this for reference as we go along. But we're going to see if this changes the number of colors that we use. Because everything is staying the same, remember, except for our order. So let's go ahead and start with our graph number 1. And as we remember from before, we're starting at vertex I, because we're going in reverse order, and there's no other color on the graph, so we start with our first legal color, which is red. So I is going to be red this time. Next, after I, we go on to vertex H, and H is touching I. So that means red, not legal. Next legal color is number 2, orange. so H is orange. After H, we move on to G. G is touching both H and I, so that means red and orange, can't use them. We have to add color number 3, which is yellow, so G is going to be yellow. After G, we move on to F. F is touching E, C, and I. So the only one we have to worry about is I, because neither of these two are colored in. So red is not a legal color, but orange is, because none of the vertices it's touching are orange. So F can be orange. After F, we go to vertex E, and E is touching a bunch of things, B, A, F, I, H, and G, but we don't need to worry about A and B because they aren't colored in. But if we look, it's touching G, which is yellow, H, which is orange, and I, which is red. So that means red, orange, and yellow are all not legal. So we have to add our fourth color, green, to our graph. So after E, we look at vertex D, all the way down here in the corner, and D is only touching H and I. And H is orange, I is red. So we can't use red, we can't use orange. The next most legal color is yellow. So D is going to be yellow. After D, we look at vertex C. C is touching I, F, and A. Don't have to worry about A because it's not colored in, but I is red and F is orange, so that means C also has to be yellow, just like D was. Only 2 more vertices left for this graph. We go to B, that's next in our reverse alphabetical order. B is touching A, E, and H. So we don't have to worry about A because it's not colored in. E is green, so green we can't use, and H is orange, so orange we can't use. But our first legal color, so we can't use orange and we can't use green. The first legal color is actually going to be red. Remember, like before, how you might want to say, oh, we can't use green, the next color is going to be blue. Blue is not our first legal color. Red is actually our first legal color. So B is going to be red. And now our final vertex, A, is touching B, E, and C. So it can't be red, it can't be green, it can't be yellow. Red, green, yellow. So our first legal color, like how we skipped around, our next legal color isn't going to be blue, like how we thought in our last one. It's going to be orange, because the only things it can't be are red, yellow, and green. So the first legal color is going to be orange. So let's go ahead and color that orange, and then like before, we're going to go ahead and number all of our vertices based on their color. So red is number 1, orange is number 2, yellow is number 3, and green is number 4. So by reversing the order that we went on this graph, we actually got one less color than we did when we went alphabetical order. So that just shows you how much order matters, and that the greedy coloring algorithm it's not guaranteed to give you the lowest number of colors. Sorry. Because order was the only thing that we changed. So that's something that we can keep in mind moving forward. But let's see how the reverse order affects graph number 2. So same thing we did in graph number 1. Just we're using reverse alphabetical order. So we are going to start with vertex E, because we don't have I, G, H, or F in this graph. So we start at E. And there's no other colors on the graph, so our first legal color is going to be red. After E, we look at D. D is touching E, so red is not legal. And the next most legal color is orange. C is touching D and E, So it can't be red, it can't be orange. Next legal color is yellow. Yellow. B is touching E, D, and C. So no red, no orange, no yellow. Next legal color is green. And finally, vertex A is touching B, C, D, and E. So it cannot be red, orange, yellow, or green, and we have to add our fifth color, which is blue. So we're going to number our colors. Red is 1, orange is 2, yellow is 3, green is 4, and blue is 5. So reversing the order didn't matter with this graph. We still ended up with 5 colors. And we can get into the reason for that after we do question number 3. But this just helps show us that the order really does matter when you're using the greedy coloring algorithm, and that you're not guaranteed to get the lowest possible color number on your first try. But let's move on to question number 3. And question number 3 is different than questions 1 and 2. It's asking us to find the size of the largest clique, which is a collection of vertices all mutually adjacent to each other, meaning each vertice is touching all the other vertices. And the largest degree, find the size of the largest clique and the largest degree, and use these to find the upper and lower bounds for the chromatic number of each graph. So I told you what a clique was, and the biggest clique of a graph tells us we need at least that many colors. And then we remember what a degree is from previous lectures, but it's how many edges are touching a vertices. So this one would have a degree of 4 because there's 4 edges touching that vertex. And then upper and lower bounds. The upper bound, actually I'm going to explain chromatic number first. So chromatic number is the smallest number of colors needed to properly color the vertices of the graph. And that can be at most 1 plus the highest degree in the graph. So these words, at most and at least, they relate to upper and lower bounds. So at most means the cap. So that's going to be our upper bound. 1 plus the highest degree in the graph is our upper bound. And our lower bound, at least, means that's the minimum that a number can be. So that's going to be our lower bound of our graph. So if we look at graph number 1, the same one that we've been working with this whole time, let's try and find the clique of our graph. So I'm going to switch colors real quick here. I'm going to pick vertex I first. Remember, the clique means each vertex has to be touching all of the other vertexes in the graph, all the other vertices in the graph. So let's start with vertex I, simply because of how many other vertices it's touching. And then I is also touching E, which is touching, if we look at E is touching a lot of other vertices too. So let's start there. E to I. Oh, sorry. And then what else is our E and I also touching? Well, E and I are also touching F, but F is only touching C, and E is not also touching C. So, and I think there's other vertices that will give us a better result. So we'll keep F in the back of our heads, but let's try some other vertices. If we look at what else E and I are also touching, they are both touching vertex G. And so right there we have a little clique. But let's see what else. If we look at vertex H, E, G, and I are all touching H. And H is touching all of the other vertices. So this right here is going to be our clique, which is remember, that tells us there has to be at least as many colors in this click in our whole entire graph. So if we treat it like we've been treating our other graphs, and let's say we just start with E is touching, and then we start with E because red was our first color. If we move to G is touching E, so it can't be red, so it has to be orange. And then H is touching G and E, so it has to be yellow. And I is touching E, G, and H, so it has to be a new color, and we're going to make it green. So this click has 4 colors. So that means our whole entire graph, this whole entire graph right here, has to have at least 4 colors. So our click has 4 colors. And remember, at least means minimum. So we're talking about our lower bound. So our lower bound is 4. Now for our upper bound, remember, it's 1 plus the highest degree in the graph. So let's take a look at some of our vertices and see if we can find which one has the highest degree. Let's start with I because we know it's touching a lot already. I has 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 edges touching it. So it has a degree of 6. And then let's look at E just to compare to see if the degrees vary at all. E has 1, 2, 3, 4, 5, 6. E also has a degree of 6. So we're going to go around and add all of the degrees just to make sure we have the highest one. A has 1, 2, 3. We won't write them down if they're lower than 6. C has 1, 2, 3. F has 1, 2, 3. B has 1, 2, 3. G has 1, 2, 3. H 1, 2, 3, 4, 5. And D has 2. So 6 is our highest degree. But that is not our upper bound. Remember, our upper bound is the highest degree plus 1. So our upper is actually 7, because we want to do 6 plus 1 equals 7. So to make this mean something to us, if we write it as an inequality with our lower bound 4 and our upper bound 7, our chromatic number, which remember is the smallest number of colors needed to properly color the vertices of the graph, is going to be between 4 and 7, or equal to 4 and 7. And we know that because the click gives us the number of colors that our graph needs to have at least, so our lower bound, and the 1 plus the highest degree in the graph gives us the number of colors at most, like the worst case scenario it could be. So we know our chromatic number has to be either equal to one of those numbers or between them. Now let's look at graph number 2 and see how this works. So we're looking for the biggest click again. And if you remember, in questions 1 and 2, we had to have 5 colors every time, and each vertex had to be a different color. And the reason for that is because our whole graph is a click. So the biggest click in the graph is the graph. And we know this because A is touching all of the other vertices, B is touching all of the other vertices, C is touching all of the other vertices, D is touching all of the other vertices, and E is touching all of the other vertices. And remember, that's what a click is, a collection of vertices all mutually adjacent to each other, or each vertex touches all of the other vertices. So for this graph, the whole graph is the clique. So that means when we are figuring out the lower bound, we again are going to look at all of the colors that it's going to take, but we know that this graph has each vertex is a different color. It has to be, because we've done that in questions 1 and 2. So we know B has to be orange because it's touching A, which is red. C is touching B and A. D is touching C, B, and A. And then E is touching A, B, C, and D. So that means our clique has 5 colors in it. And that means our lower bound is going to be 5, because that's the minimum amount of colors that our graph has to have. And then for our upper bound, all of our vertices are touching each other, right? We know because the graph itself is a clique. So that means they're all going to have the same number, the same degree, because they're all touching the same amount of vertices. They all have the same amount of edges coming out of them. So 1, 2, 3, 4. A has a degree of 4, which we can write down. And we can show that all of the other vertices have a degree of 4. So B has 1, 2, 3, 4 edges coming out of it, so it's got a degree of 4. C has 1, 2, 3, 4. So it's a degree of 4. D has 1, 2, 3, 4. E has 1, 2, 3, 4. So all the vertices have a degree of 4. And so that means that's not our upper bound, remember, because our upper bound is 1 plus the highest degree. So it's actually 5 as well. So our lower bound is 5. Our upper bound is 5. And the chromatic number, being the smallest number of colors needed to properly color the vertices of the graph, is between or equal to 5 and 5. So what does that mean? We can't really have a between 5 chromatic number. We can't have 5.5, because you can't just color half a vertice or half a vertex. So really, what this is telling us is that our chromatic number is 5, because if it's greater than or equal to 5 and less than or equal to 5, that means it has to just be 5, because we can't have a between 5 chromatic number. So if we look back at our graphs and compare that to what we found here and here, we know that graph number 2's chromatic number is 5. So our first attempt using the greedy coloring algorithm gave us the chromatic number, because we know it's 5. And our second attempt with the greedy coloring algorithm with reverse alphabetical order gave us 5, and we know that's also the chromatic number. But for graph number 1, the chromatic number could be between 4 and 7. So 4 being the smallest that it could possibly be, and 7 being the biggest that it could possibly be. So our first graph gives us 5. And we know that's within the range, within our upper and lower bounds. But we can see with our attempt number 2 that 4 is a possibility. And 4 is the smallest that our our chromatic number could possibly be. So 4 must be our chromatic number. And so using the greedy coloring algorithm with reverse alphabetical ordering gave us our chromatic number, but using it with alphabetical ordering did not give us our chromatic number. And remember, we know that 4 is the chromatic number because we successfully did it, and we know that 4 is the lowest that it could possibly be. So that's pretty much everything. I hope you enjoyed listening to me. I'm grateful that you came and listened. I hope you learned something new, and I will see you next time. Bye.